Welcome to section 2.4. We are today going to study some elements that are related to what you've seen in pre-calculus and kind of push them further. There's also going to be an important theorem for AP Calculus AB in the year. There's 4 theorems that we need to know, and one of them is called the intermediate value theorem, and we're talking about this right away today. So, the definition of a function that is continuous, if we use the concepts we've learned about limits, is the following. Firstly, we need the point at which we are trying to see whether f is continuous. We need that point to be defined. Secondly, we need the limit as we approach that point to exist. And finally, we need both of these to be equal. So it's really nice to see examples that are actually showing when one of these 3 requirements is missing and see how that affects the function, or how it potentially affects the function and makes it not continuous. So there's 3 conditions for which the graph of f is not continuous at C. So we're going to first look at what happens if f of C is not defined. Here's what happens. You would have a hole, so condition 1 is not satisfied, and you can see f is not continuous. What happens if f is continuous, but this time it's the limit of f of x as x approaches c that does not exist? That's what it looks like here. We approach a certain value from the right, we approach a different value from the left, so the limit does not exist, and clearly this function f is not continuous. Finally, we may have 1 and 2 that are both satisfied, but they do not agree together. And this is how it could happen. F of c is defined, it's down here. The limit as x approaches c is this value there, but they are not the same. So once again, in that case, the function is not continuous. So you really need all of these 3 requirements, and when you do an exercise you need to verify each of these in order, and if all of these are satisfied, then you can confirm that the function is continuous. What we saw above was continuity at a point, so we were looking at one point and seeing if it was continuous. If we are wondering about an open interval, so a whole span of values, then technically, we can just say that the function is continuous on that interval if it's continuous at every point in the interval. This is specifically for open intervals. We'll talk later about closed intervals. Okay, now we can classify discontinuities into 2 ways. One of them is to say that they are removable, and one of them is to say that they are non-removable. So imagine that you had one superpower that you're probably going to be disappointed with if you look at all the superpowers that superheroes have, but your superpower is that you can move 1 point on a function vertically, or you can add a point if there is none. So if with this superpower you can change a discontinuity, a function that is not continuous, into a function that is continuous, then we say that this discontinuity is removable. If, using that superpower, you're still not able to change the not continuous function into a continuous one, then we say it's a non-removable discontinuity. For example, here in A, we have the function f of x equals 1 over x. The discontinuity is at x equals 0. There's no way that by adding just 1 point along this vertical that I'm going to be able to connect the 2 branches of the function. One is going down here, on the other side it's going up here. I can't connect them with just 1 point. So this is a non-removable discontinuity. However, in example B, we have a removable discontinuity. You might be able to recognize that here this is almost like the function y equals x plus 1, except that there is a hole at x equals 1. Now I can, with my superpower, just add the point and fill in the hole. And now that I've done that, this function would be continuous. So that is a removable discontinuity. Last type of example that we will see. If you have a function that is defined like that, there are two rules. One rule is for all the values of x that are not 1, and one rule is for x equals 1. We call this a piecewise function. What it looks like is something like that. It's a whole, but you can see that there is a point at x equals 1. It's not quite the same as here. However, my superpower allows me to move a point and place it somewhere else vertically. So now, with my superpower, I can again fill this hole, and the function will be continuous. So it's a removable continuity, a discontinuity at x equals 1. So a reminder, a one-sided limit is when you look at a limit but you only analyze it from the left or from the right. When we talk about a limit, it's kind of taking both together. So the limit of f of x as x approaches c from the right, we write it like that. This is the important part. There's a little plus, so it's x approaches c from the positive side. Remember that the axes have an arrow that points to plus. So if we approach from the plus side, it means we approach from here. And likewise, if we approach from the left, we write that it's the limit as x approaches c from the left, from the negative side. The greatest integer function is a function that is quite popular in AP Calculus AB or pre-calculus when we study limits. What you do is, well, what it is, the greatest integer function, is that for any input value x that you put in, the output is going to be the integer that is closest to the input, but lower. So for example, if I input 4.37, the closest integer that is lower than that is 4. If I input 12, then it's 12. Yes, I should have said it's lower or equal. So f of 12 equals 12. If I input negative 5.2, then the value of the greatest integer function is negative 6. Be careful, don't think you just truncate the decimal, because we have to take a value that is lower. So what is lower than negative 5.2? It's going to be negative 6. What the graph looks like is these steps, which is why sometimes we call this a step function. And you can see that it has lots and lots of discontinuities. So it's quite interesting. And these are non-removable discontinuities. I can't just put one point in between and connect two of these steps together. So if we look at the graph from the previous page, we will be able to answer this question. What are the one-sided limits as x approaches 0 for this function, and determine whether the limit as x approaches 0 exists or not. Finally, there's an extra question that is rather difficult. On what intervals is f continuous? So going back to the graph, if x approaches 0 from the right, we are approaching here, then the limit is going to be 0. On the other hand, if we approach from the left, so we're approaching this way, trying to make an arrow, we are approaching the value y equals negative 1. It might be a little bit weird because sometimes when we have limits, y varies and you can actually say it approaches the value. Here y equals negative 1 the whole time, but then it's also approaching negative 1 if it's already negative 1 and not moving away. So conclusion, from the right the limit is 0, from the left the limit is negative 1. Limit as x approaches 0 from the positive side of f of x is 0. From the negative side, it's negative 1. Since these two values disagree, we conclude that the limit as x approaches 0 of f of x does not exist. You can always write DNE, that is an accepted abbreviation for does not exist. And now let's see the second question. On what intervals is f continuous? It's not very easy to express, but you can see that it's always continuous from here to there. This endpoint is included, that one is not. And then it starts again for the next integer. It's going to be continuous from here to there. So it's continuous if we only focus on positive values from 0 to 1, from 1 to 2, from 2 to 3, and always the beginning is included, the end is not. So how can we express that? Here's one way of doing it. F is continuous on all intervals from n to n plus 1, where n is an integer. There's a little e missing here. So let's pick a random integer, for example, n equals negative 24. Then it says that f is continuous on the interval from negative 24 to negative 23. And that is true whatever n I pick. Now, what's the difference with a closed interval? We said earlier that a function was continuous on an open interval if the limit existed for each point. This is still true for the closed interval. However, we have two little problems, and these two little problems are the endpoints. Why? Because when we focus on, let's say, this endpoint here in this example, I can't talk about the limit from the left. And normally when we just say limit, we mean the limit from the left and right together. So I just have to make this little exception that for a closed interval, it's going to be continuous if it's continuous on the open interval, and also for the two endpoints, we only look at one side. So for that endpoint, we just focus on the left side being continuous, and from that endpoint, we want the right side limit to approach the value. Discuss the continuity of this function. It's shown here, so we all know now that it's a semicircle. Why is that? If this is y equals 4 minus x squared, you can take the square on both sides and you'll get y squared equals 4 minus x squared. And then if you add x squared on both sides, you will see that it's the equation of a circle, x squared plus y squared equals 4. Now it's only a semicircle because it's not plus or minus the square root. We only look at the positive square root. So how do we discuss the continuity? We need to do the two steps above. First of all, we need to agree that f is continuous on the open interval from negative 2 to 2. And then we need to look carefully at each endpoint and say that yes, for x approaching negative 2, from the positive side, so when I approach from the right, I'm going down like this. So limit as x approaches negative 2 from the positive side, it is going to approach the value f of negative 2, which is 0. And second part, I need to agree that when we approach x equals 2 from the negative side, so limit as x approaches 2 from the negative side, we are approaching the value of f of 2, which again is 0. So continuous functions are well behaved. When they are put together, you can add two continuous functions and it will remain continuous. You can subtract functions and they will remain continuous. If you multiply two continuous functions, they will remain continuous. If you divide two functions, it will remain continuous, except if g is 0, then there's a big problem. And finally, you can just multiply a function by a constant, and that new function will also be continuous. So you can play with continuous functions and it will stay continuous. That's an example. Who would guess that this is actually an easy answer? This is a continuous function, even though I have no idea what it looks like, just because each of the parts, y equals x, y equals sine x, y equals x squared, y equals 2, y equals the absolute value of something. All these things are continuous, I know it. So when I combine them, it will still be continuous. Finally, the list above didn't include compositions of functions, but compositions of functions are also continuous. There's just a little bit of a subtlety. G needs to be continuous at C, and F needs to be continuous at G of C in order for F of G of C to be continuous. Okay, so let me just include that little bit. We're now going to talk about the intermediate value theorem, which is one of the 4 theorems we see this year in AP Calculus AB. And I think intuitively, it's something we really can understand, but the way we write it in math sometimes kind of muddies things a little bit for students. The idea is, if you have a continuous function from x equals a until x equals b, so this is a continuous function on the closed interval ab, then whatever value I choose on the y-axis between f of a and f of b, I can always be certain that there is a point C where f of c equals k. All right, I could have chosen k down here, and I would again have been able to find a value c, I'm guessing at this time it would be here, where f of c equals k. This is just what the intermediate value theorem tells us. Whatever value you choose between the two outputs, it is always going to be possible to pick an input such that f of the input gives the output you picked. On the other hand, sometimes, like if I choose a k here that is not between f of a and f of b, we can see that we don't find a c in this interval such that f of c equals that value. If I happen to pick it down here, well, I'm really lucky. This time there is a c. I could choose c here, and I could have f of c equals k. So that can happen, but it's not because it can happen that it must happen. And the intermediate value theorem is about something that must happen. So let's read the mathematical definition. For any number k between f of a and f of b, there exists at least one number c between a and b such that f of c equals k. So the IVT assures us that c exists, but it's not a very powerful theorem. It doesn't help us to find where c is. It just tells us, it just makes a promise, yes, c exists somewhere between a and b. Moreover, the IVT tells us that there's at least one c, but maybe there are more. Who knows? If I had a function that did like that, then I would have many values of c that I could pick such that f of c equals k. So there's at least one. You can see how it's important that the function is continuous in order to have this theorem be applied, because in an example like here, where I have a function that is not continuous, then between f of a and f of b, if someone picked that value k, then I wouldn't be able to find c here such that f of c equals k. So we must check that a function is continuous before we apply the theorem. For instance here, prove that this function here has at least one zero in the interval 2, 4. So firstly, I need to check that f is continuous on the interval 2, 4, and yes it is, because x cubed is continuous, sine x is continuous. Secondly, if I have a calculator, I can find that f of 2 equals 7.2 approximately, f of 4 equals negative 48.4 approximately, and now I can conclude. I can conclude that according to the IVT, there is at least one value c between 2 and 4 such that f of c equals 0. If we started here and we ended down here and the function is continuous, we must cross the x-axis somewhere. That's what it says. As you notice, it doesn't tell us where, but it just promises us that it exists. So that's it for section 2.4. Thank you.